Continuing in section 13.6, we're looking at the gradient of a function. This slide shows the definition of a gradient function of two variables, where z is a function of x and y, and the partial derivatives with respect to x and y both exist. Then the gradient of f is denoted by this symbol here. It's read as del f. So the gradient of the function of xy is the vector, which is equal to the partial derivative with respect to x of that function I plus the partial derivative with respect to y of that function j. So another notation that you'll see is the actual bold GRAD for the gradient. Okay, it is important to know that the gradient is a vector in the plane. It's not a vector in space when you're looking at a function of two variables. For a function of three variables, the gradient is found by taking the partial derivative with respect to those three variables, and those are the components of the vector in space. Now, gradient in this picture illustrates a surface, which is a function of two variables. You can calculate the gradient at a specific point. Now, again, this is a surface in space, but the gradient ends up being a two-dimensional vector, a vector in the plane. In this example, we're finding the gradient of f of xy equals y natural log of x plus xy squared at the point 1, 2. Again, using the definition for a gradient, the gradient is going to be a vector where you're using the partial derivatives with respect to x and y as the components of that vector. So if you take this function and take the partial derivative with respect to x, you're going to treat x as a variable and treat y as a constant. So the derivative of y times the natural log of x is going to be y times 1 over x, or yx. And the derivative of xy squared, where you treat y as a constant, is y squared. Now you want to take the partial derivative of this with respect to y. Treat y as a variable and treat x as a constant. The derivative of y natural log of x is y times that constant, or the natural log of x, plus the derivative of xy squared, treating y as the variable. That derivative is 2xy. So the gradient of this function of two variables is a vector in the plane, where the partial with respect to x, I, plus the partial with respect to y, j. Now we're going to evaluate it at the point where we can plug in 1 for x and 2 for y. So by plugging that in, you can simplify to get the vector 6i plus 4j. So again, this function of two variables represents a surface in space. The gradient is a vector in the plane. Okay, for this example, we're given z equals natural log of the quantity x squared minus y. Find the gradient at the point 2, 3. The formula is given here for you, so you can take the partial derivatives with respect to x and y, and then plug in the values 2 and 3 for x and y to evaluate the gradient. Try this one on your own, pause the video, and then come back and check your answer. Okay, to find the gradient, we are going to take the partial derivative of this function with respect to x. Now the derivative natural log of u is u prime over u. We're going to treat x as a variable and treat y as a constant. So the derivative of x squared minus y with respect to x is 2x, and you're going to divide that by x squared minus y. It's going to be your first component of your gradient vector, plus the partial derivative of this with respect to y. You're going to treat y as a variable and x as a constant. So the derivative of x squared minus y is negative 1, and we're going to divide that by x squared minus y. That's your j. So that would be the gradient, the general equation for the gradient vector. Now we're going to find the gradient, evaluate it at the point 2, 3. So the gradient of the function at the point 2, 3, we're going to plug in 2 for x, and we're going to plug in 3 for y. Okay, and that will simplify. We're going to have 4 minus 3, 1 in the denominator, 4i, and 1 over 2 squared minus 3, we're going to get minus 1j. Alright, so that's the gradient of z at the point 2, 3. This slide shows applications of the gradient and other properties of the gradient. If the gradient of the function, in this theorem, theorem 13.11, number 1, if the gradient of the function is equal to 0, then the directional derivatives, looking in any direction of the function, equals 0 for all unit vectors. For number 2, again, we're looking at a function, and the direction of the maximum increase of f is given by the gradient of the function. So that gradient is pointing in the direction. It is pointing in the direction of the maximum increase. And the maximum value of any directional derivative is the magnitude of the gradient function, the gradient of the function. The direction of minimum increase of the function is given by the opposite of the gradient of f of xy. The minimum value of any directional derivative is equal to the opposite of the magnitude of that gradient. So the first theorem applies if you have a function of 2 variables. This portion outlined in the bottom here, that's extended to a function of 3 variables. A property here we see in number 1 is that the directional derivative is actually found by taking the gradient with the dot product of the unit vector. And also, again, if the gradient is equal to 0, then the directional derivatives will all equal 0. And again, number 3, the direction of the maximum increase is given by the gradient, and the maximum value is the magnitude of the gradient. And then the direction of the minimum increase of f is given by the opposite of the gradient of our f of x, y, z. The minimum value of that directional derivative is the opposite of the magnitude of that gradient. I went back a few slides to near the beginning to show you how you can interpret those properties. Again, the gradient is a vector. It's pointing you in the direction. In fact, it's pointing you in the direction of the greatest increase. So suppose you're sitting here on this hillside right here, and you want to look in the direction where the slope is the steepest. Where is the elevation changing most rapidly? So if you're right here, you would probably be looking up in that direction. Okay, if you look in any other directions, it's not going to be as steep, the slope. The maximum value of any directional derivative is going to be the magnitude of that gradient. In this example, we're going to look at another interpretation of the gradient. The temperature in degrees Celsius on the surface of a metal plate is given by this function of 2 variables. T of xy equals 20 minus 4x squared minus y squared. And x and y are measured in centimeters. So we have a flat metal plate, and you can measure the temperature given the coordinates on that metal plate. In what direction from the point to -3 does the temperature increase most rapidly? And what is this rate of increase? So we want to look in the direction. You're at a point to -3 on the metal plate. You want to know what direction is the temperature going to increase most rapidly. Well, that direction can be found by finding the gradient. The gradient will give you the direction of the greatest increase. And in this case, it's going to be the increase in temperature. The actual rate of increase is found by taking the magnitude of that gradient. So the gradient is found by taking the partial derivatives with respect to x and y. We treat x as a variable and y as a constant. That derivative is negative 8x. And when you treat y as a variable and x as a constant, the partial derivative with respect to y is negative 2y. Now we're going to plug in the point given, 2 for x and -3 for y, and plug that into the gradient. We will find that that gradient is the vector -16i plus 6j. So at this point here, 2, -3, we find the gradient vector. It's a vector in the plane. It is pointing in the direction of the greatest increase in temperature. To find that rate of increase, you're going to take the magnitude of the gradient vector. So if our gradient has components -16, 6, the magnitude of that would be the square root of, take -16 and square it, and 6 and square it, add those together to get the square root of 292, or approximately 17.09 degrees per centimeter. So looking in all the directions, it appears like that plate is the hottest right close to the origin. So if you're at this point, you want to look at the temperature of the greatest increase. It gets hotter and hotter as you approach the origin.